On a glacier, you have different materials. You have liquid water, and you have solid water. And solid water can be divided into snow, firn, and ice. And there's a big difference between those three materials. It's their density. If you take the accumulation area of a glacier, when let's consider you have like a nice storm and snow is falling on the ground, then you'll have material with a pretty low density, as we saw 0.1, 0.2. And as these materials get buried, as time passes, it will kind of lose its shape. Like think of nice snowflakes that have good symmetry. And imagine you're trying to build a house with each individual snowflakes. They do not superpose well with each other. But now that the snowflakes are losing their shape, they're kind of rounding up, they can be imbricated in each other much easier, so you can fit more material into the same volume. That's the process of densification, which we also call metamorphism in that case. So the snow is transforming into firn, and firn is snow that persisted for at least one summer. And firn represents the intermediate stage between snow and ice, as I said in the previous video. We consider that we have ice whenever the air bubbles that are into our material are trapped. They cannot escape. When you have firn, you can still have that air escaping the material, and it becomes ice as soon as the air is trapped. So we already have a process of densification from the top of the column. If that's let's say the surface of the glacier. At the very top, you have snow. It gets denser, transforms into firn as it has survived a summer, and eventually becomes ice at some point. So that transformation process is called metamorphism. Metamorphism means that the material is going to transform into something slightly different with a different density, for example. As snowflakes fall on the ground, they have a very nice shape, six-fold symmetry, and they will get kind of broken, beaten up, melt away a bit. They will basically lose their nice shape and become more rounded. When they're pretty rounded, they are considered to be firn about 60 days or something like that after the snowfall. And after time, as they get buried under more and more snow, it transforms into glacier ice. So you have really, metamorphism is controlled by all that compaction that you have by adding material on top of your layer of snow. Melt refreeze of those ice crystals, because as they melt, they kind of round up naturally. And that is depending on the humidity and the temperature inside your snowpack. There's a very cool lab video that you'll have about this topic in particular. And that's kind of explain why you have such different snow types when you look at the snow that's outside in Fairbanks. You have sometimes something very powdery outside, and if you dig into the snow right at the bottom of your snowpack, you might have very different ice crystals that look much more defined. That's super important when you go skiing outside, because the presence of crystals like that might mean that the snowpack is unstable and therefore much more prone to create avalanches. So there are basically two types of metamorphism: dry metamorphism and wet metamorphism. Dry metamorphism means that no melt is occurring, and it's mainly the fact that you bury your snow layer that it will increase the compaction. It will break away the snowflakes, and therefore they will stack on top of each other there much more easily. Wet metamorphism, on the other side, will round the ice crystals and make them bond together much more easily. So that's also a process that increases density. So both dry and wet metamorphism are processes that increase the density of snow that eventually leads into firn and therefore into ice. I'm drilling those concepts into your heads because that's super important. You can measure snow and firn density by, for example, digging a snow pit and taking measurements at different parts of your different heights in your snowpack. And it's quite funny to do. Whenever you are in your snow pit, you use one of those devices. You know the volume of that. So basically, you sample a known volume of snow, and then you weight it. And because we said that density was equal to the mass over the volume, we get the density of our material by weighing how much the volume we sampled weighs. If you do that, if you do a snow pit and measure the density in that snow pit, then you might end up with that kind of figure that shows that as you go deeper and deeper in the snowpack, the density increases. And eventually, if you go to the ice, well, the density will be about 0.9. So we have here a nice figure representing the fact that here, that's the top of the snowpack. Here, that's the bottom. We first have snow with pretty well-defined snowflakes. As you go deeper, they are losing their shape, becoming a bit more blurry, and the density increases, and then they become super rounded. And once they are rounded, it's only a matter of time until they become ice. And the last slide for this section is kind of showing you can see with your eyes the differences in the snowpack. And for example, having inclusions, for example, of melt layers into the snowpack, meaning that at a very specific time, you had snow that melted, probably because it was warm enough during the day. Then you have what we call an ice lens. You have a layer of ice in your snowpack that will change the density of the snowpack, and you have to take that into consideration. I'm talking about all of that because when we are studying glaciers that are very big, or not necessarily big glaciers, but any glacier, when you want to know how much ice is being created, you have to measure the thickness of the snowpack. And having the thickness gives you an idea about the volume of snow you have on your glacier, but knowing the density of that snowpack, then you can calculate how much water equivalent that represents. And therefore, you can tell, well, my glacier is losing more ice than it's actually creating some. So this glacier, for example, is disappearing, stuff like that.